I welcome you all to the second lecture of Geophysical Inversion. Today we will talk about the various geophysical methods which are used to study the subsurface and some common terms which should be known while doing geophysical inversion. Okay, so Earth system is inherently complex, we all know that. Now in today's world, the neural networks are being applied in different fields at different levels in all the dimensions because they are universal approximators. Why they are universal approximators? It is because they can learn complex functions by making them piecewise linear or non-linear functions. Okay, so for example, sigmoid function, tan hyperbolic function, Rayleigh function, etc. We'll talk about them later in the lectures. Now geophysicists are also like neural networks. Okay, why? Because Earth is very huge. So for example, this diagram denotes various layers of the subsurface of the Earth, and the radius of the Earth is about 6,378 kilometers. Okay, so here what we see is the uppermost layer is the crust, which is around 35 kilometer in thickness. Even in the crust we have two distinctions, one is continental crust, another is oceanic crust. And in the oceanic crust we have a Conrad discontinuity which does not exist everywhere. Okay, on continental crust we will see mountains. So the Earth which we see today is a result of process which has been ongoing for billions of years. Okay, so the oldest deposition or the land formation, if we want to see, that is usually seen in continental crust, and the oceanic crust is comparatively new, okay, young comparatively. It is on a scale of millions of years. Then between crust and mantle lies the Moho discontinuity, which is marked as an abrupt change in the velocity. Seismic studies are done, and that helps to map the Moho discontinuity, which is at around 35 kilometer, but its depth might vary depending upon whether the region is in the continental crust or oceanic crust. Okay, it might go to 50 kilometer as well on the continental crust. Then we have the upper mantle and lower mantle, and then there is a repeated discontinuity which marks the change in the density. Okay, then we have a Gutenberg discontinuity which lies at the boundary of outer core and the lower mantle, and then we have Lehman discontinuity which lies at the boundary of outer core and inner core. So to study all these layers we use seismology, which deals with the study of the subsurface of Earth using earthquake signals. Okay, and then we have magnetotele methods. But when I say we are like neural networks and we are learning things piecewise, it means that we are breaking down these structures and trying to estimate the top 10 meter, top 100 meter, top 1 kilometer, top 100 kilometer, top 1000 kilometers, and then we are using various geophysical methods to understand these subsurface at different scale. Okay, next important aspect is that Earth acts as a low pass filter, attenuating high frequency seismic waves. So the consequence of that is that the subsurface resolution which we need is lost when the high frequency is lost. To understand this, we can see in this diagram that this top image in the left side shows the seismic section, the right side shows the amplitude spectrum. Okay, so this axis is talking about the energy or power, and this is talking about the frequency in hertz. In the seismic section, this scale talks about the time in millisecond, and this is basically the reflectivities or the amplitudes. And you can see that around 1000 meter here in this section, there is a thick black color layer. Okay, it is at around, let's say, 900 millisecond. Okay, and the frequency content of the signal is up to minus 30 decibel of at around like 60 hertz. Okay, or let's say, okay, and as we increase the frequency content in the signal using the inversion algorithm, so we have got well log data and we have got seismic data, and we combine both of them during inversion to enhance the frequency content of the seismic signal, and this is what we get. Okay, so now you can see at 100 or at 1000 millisecond at around, we have got more clarity with respect to the reflectivity. If this is a colored section and this is an uncolored section, again black and white section, and hereby a filter has been a bit applied, that's all has been done, okay, to smooth out the frequencies or this loss of the signal which is there, that has been enhanced. Okay, so what you can see here is that at around 1000 meter, now instead of seeing just one black line which was thick, we can see two thick black lines. And usually the seismic velocity is, let's say, even if it is 2000 meter per second, so this thickness of line is might correspond to 20 meter change in 20 meters. So the uncertainty with which we are predicting the depth or the thickness of a layer might vary by such a large amount because by the help of high frequency we can reduce that uncertainty. Okay, so that's why we need high frequency information as well. Next, what I want you to understand is that since Earth has different layers, there are different properties also which we are studying. So for example, near mid-oceanic ridge, the mantle is warm and there is a volcanic eruption which is going on. The ocean crust is moving along the left and right direction, leading to the formation of anomalies which are magnetic in nature, and they are alternating bands of normal and reversed polarity, whereby it was seen around in 1960 during magnetic survey, which proved that during the evolution of the Earth, the magnetic field of the Earth has reversed. Okay, so basically what I wanted you to understand through this example is that geophysics is not used just to locate resources, okay, but also to understand the geological process which Earth has undergone in order to understand the evolution of the Earth in the coming time. So for example, Himalayas, right, they are continuously increasing in height. There is certain kind of uplift which is taking place, and below, if we see, the Indian plate is getting subducted beneath the Eurasian plate. Okay, so here's a question for you all, you can answer it in the comment, that what is the speed with which the Indian plate is moving or colliding towards the Eurasian plate. Okay, and this is also studied with the help of geophysics also. So that's why there are so many earthquakes which are happening and people are studying it all over the world. Next, there are geophysical exploration methods which are categorized into active methods and passive methods. So under active methods, we all know now from previous lecture that source is under our control, it is man-made. And so for example, we have got seismic, there is a refraction method which is used at continental scale to map the moho, or it might be also used to map the basement rock, okay, depth. Then we have got reflection studies which can be done for oil exploration, mineral exploration, groundwater exploration, etc. Then we have multi-channel analysis of surface waves. It is also used a lot in construction industries before building of dam or any build. It is cheap and very fast. It gives the shear wave velocity information as well as if there is a fault that is present in the subsurface. So the depth of investigation obviously varies from tens of meters or tens of meters to even kilometers. Okay. Then we have got DC resistivity, basically direct current resistivity, Resistivity method excels in resistive environments such as igneous rocks with low porosity and permeability. Okay, it helps to map the top 50 meter of the subsurface, and basically we have got electrodes which we put inside the uh, earth, and then we try to measure the current which flows. Then we have got induced potential. It has higher depth of investigation that can go up to 600 meter as well in some cases. So in the induced potential method, basically we try to not only map the ore bodies or the conductive minerals like sulfide or graphite, but it is different from resistivity method in the sense that it reacts to the electrochemical properties of the subsurface. Okay, then we have got electromagnetic method. Okay, it is useful in areas with high conductive zones. Okay, and rough terrains if we have, then we can go for aerial electromagnetic exploration, and it helps also to map up to thousands of meters. Okay, then we have control source, MT, and magnetotelluric and electromagnetic methods. They have limited use, but they are right now used rigorously for geothermal exploration. In hydrocarbon setting also it was used. Then basically then we have got passive methods. In passive methods we have seismology and passive seismic method. In seismology we study the earthquake signals to map the crust, moho, mantle, core, what we have seen earlier. Using the magnetotelluric method also we can map up to thousands of kilometers below the subsurface. And what is the source of signal? The source of signal is basically the thunderstorm activity and interaction of solar wind with Earth's magnetosphere, and the magnetosphere is lying 65,000 kilometers above the surface of the Earth. So imagine something which is 65,000 kilometers above the Earth is having an impact such that we are able to use the subsurface of the information of the Earth which is lying thousands of kilometers down. Okay, so that is the power of geophysics. Then we have got gravity method, whereby we study the variations in the subsurface gravity, and it is used in iron ore, copper ore exploration. It is also used to monitor glacial mass change. Magnetic anomaly study is done using magnetic methods, and it is, I already gave you an example as well. Okay, then we have electromagnetic very low frequency method. Again, it is used for crustal mapping. We have got self potential method, which is used to map natural electrical potential variations due to groundwater flow or mineral deposit, or maybe some other subsurface process. But it is not used nowadays a lot because we are trying to understand more complex geology, and the signals of the passive method is usually weak and we need higher resolution. So induced potential is used in place of self potential in many cases. Obviously it also depends upon the budget. Then we have got nuclear subsurface investigation, in which there are many well logging tools which are there. What happens is there is a well, so basically the instrument such as the gamma log, neutron log, or borehole nuclear magnetic resonance logs, these kind of logs are read through the instruments which are put inside the borehole, and they have a resolution of even of centimeters. Okay, so we can see that we have got different kind of methods, and in all the methods we have to do inversion and processing to form the final geological interpretation which can be used. Okay, workflow of geophysical exploration we have already talked about. There is planning, acquisition, processing, inversion, and interpretation. So now what I would like to highlight here is that since we have seen there is complicated geology, okay, and so there are chances that one method might not be able to do full justice to form the full information of the subsurface. So many a times we have two methods which are used to study a region. Then we combine the physics of the two methods and do the inversion together, which is called as joint inversion. Okay, and in many cases what we do is that we have got different geophysical methods. We have done the inversion of that, and while interpreting we combine the understanding through every inverted subsurface information, for example resistivity, vp velocity, density and magnetic values, and then we try to form the complex geological story of whatever exists beneath the subsurface. Okay, now as we had talked about that earth acts as a low pass filter, so it is important to understand what is the consequence of that. So we can map the subsurface in basically in if we are trying to map the top surface, let's say top 10 meter or 5 meter or maybe even centimeters, or are we trying to map the top 100 meter or 80 meters, or are we trying to map top 100 meter, are we trying to map the on a regional scale which is much larger, or are we trying to map the whole earth, for which usually earthquake signals are used. So on this vertical axis I have written depth, and you can see this arrow length is basically denoting the wavelength which is used to map the depth. So if we are mapping shallower depth, then we are using smaller wavelength. Okay, that means higher frequency, right? As the depth of investigation increases, the wavelength increases, frequency decreases, and the duration for which we need to record the signal, so that we follow the Nyquist theorem, okay, to prevent aliasing, we need to record longer. If you guys want me to make a lecture on Nyquist theorem and aliasing, you can comment it down. So what are the components of inversion? The components of inversion consist of 6 parts broadly. One is forward modeling function, second is discretization, third is initialization, fourth is loss function definition, fifth is regularization, and sixth is optimization method. So basically the forward modeling function can be also 1D, 2D or 3D in nature, irrespective of how you have already acquired the data. The acquisition can be 1D, 2D or 3D, about which we are not talking. Okay, we are talking about the forward modeling function. Okay, before that let's understand few terms. One is homogeneous. When we say the subsurface is homogeneous in nature, that means it's uniform in composition in all the directions. Okay, and that is not a reality, but when we start the planning activity or when we are doing some synthetic studies, then we always start from homogeneous case. Then comes the heterogeneous case. So the composition is not uniform in that case, and the properties will vary in all the directions, in all the locations in a given region. Then we talk about lateral variations, which is important. So variation along the horizontal direction, when we say, that is known as lateral variation in geophysics. Now anisotropy is when the property at the same location change with respect to in which direction I am taking the measurement. This happens a lot in case of mineralized zones, or in zones whereby the resistivity varies with direction of the mineral which is present in the subsurface. For example, if there is a crystal, you might have studied that in certain direction it is easier for the current to pass, whereas in an orthogonal direction the current it's more resistive for the current to flow. Okay, so same goes for seismic studies also. In certain directions it is easier for the elastic waves or elastic waves mostly to travel, maybe because there is a permeability in that zone, or maybe because the fractures are there. Okay, and in the perpendicular direction it might not be that easy. So when I'm saying not easy, that means the velocity will decrease or increase, okay, depending upon the situation. Now, so why is all this important? Homogeneous, lateral variation, anisotropy is that when we assume that my subsurface is varying only in one direction, right, just in the, if I travel vertically downward, then the properties are changing only in that direction, otherwise in the horizontal direction there is no change, then the forward modeling function which we are using, it is only accommodating for the physics change when we are traveling downwards. So that means the waves are just traveling perpendicular downward sides, right? When I talk about 2D forward modeling function, things change. Okay, so let's try to understand this more visually. So for example, this red and blue hemisphere are wavefronts. Okay, the green line represents the receiver line. Okay, so let's say this is at the surface and this green line is representing my receiver line whereby I have placed receivers, and the brown plane contains the green line and is tangent to the blue spherical wavefront. So whatever is perpendicular to this line, green line, will travel on this tangent plane, right? That we all understand. Okay, so what happens next is that if we are assuming that field is only traveling perpendicular, then this is how it looks, right? The green color. However, in reality, the wave fields are not like that. They are not going to travel like that, right? We might have certain inhomogeneity here, and the wave might be coming from this side also, not just this green, traveling in the green plane which is adjacent to this blue tangential plane, right? So that is what is seen. So there might be energy which is coming out of the plane. So that means it might not travel along the plane of this brown colored plane which I have drawn here. And when this out of plane information comes, then we need to take care of that, not only during processing but also during inversion. If my earth is let's say laterally also homogeneous in nature, or laterally they vary, properties are not varying much, then I might not go for 2D or 3D inversion. Then I will go for only 1D inversion, in which the physics will account only for the information which is traveling in this way, right? But if my function is my subsurface is such that it is containing inhomogeneities, for example, if there is a salt diaper beneath, or if there is a dome beneath, or if let's say you are traveling in this direction and there is some subsurface anomaly in this place, then obviously you will get reflections from this zone also. So for example, if you blast dynamite here, the wave will travel this way and then it will get reflected here also, right? And you cannot map this reflection which you will record on the geophone just below the subsurface. It is coming out of plane, so you have to consider that 2D and 3D aspects in the function. Okay, so in cases where Earth is assumed to be horizontally layered with no lateral variations, then forward modeling function usually might form a propagator matrix form, whereby there will be some recurrence relationship. So what happens at last layer, name, let's say nth layer, then n-1 layer, then n-2 layer to the first layer. Okay, and that is called as 1D inversion. In cases where lateral variations are there in the subsurface, the recording has been done along a line using receivers, then most of the time constraints are used along horizontal direction in order to maintain the continuity of the inverted layers, and such inversions are called 1D laterally constrained inversion. Still we are not accounting the physics of the 2D of the problem, right? Whereas when we say 2D inversion, when the process of estimating subsurface properties in a vertical plane, assuming that the earth properties vary in 2 dimensions and are constant or negligible in the 3rd direction, then it is called as 2D inversion. Okay, 3D inversion we have already talked about. The forward modeling function will take into account all the physics in all the directions, so we have got 3D wave propagation studies for that. Then there is one thing which is called as 2.5D inversion. In this case, the modeling and inversion approach is such that it is bridging between 2D and 3D methods. So data is collected along 2D profile. Model is in fact even varying in 2 dimensions. But the physics which we are using for forward modeling is accounting for the 3D effects. Okay, such as the influence of source and fields extending into the 3rd dimension, even though model itself might not vary in the x-axis direction. This is very important for you to understand. Now we have been talking about this function, forward modeling function f, a lot. So is this f function a scalar or vector or a matrix? What it is? Okay. So it is very important to understand the size and components of the Jacobian in full waveform inversion as an example. Okay, we are taking full waveform inversion as a. So let's say I'm saying that FM is simulating the seismic data. Okay, so F1 refers to the data at a specific receiver. If referring to a single time sample, in this case it will be a scalar. Okay, but if I am referring to the entire waveform at a receiver, it is a vector. So for example, if I have got two receivers, each receiver records 100 time samples, then F1 could represent the entire waveform at receiver 1 such that it belongs to a set of real numbers in a dimension of 1000. And if we take stacks from all the receivers, okay, so in this case we have got two receivers, but we all know that seismic data acquisition takes place with minimum 12 channels. In fact, nowadays it is always more than that. So in that case the size will become 2 into 1000, right? So now it's a matrix. Now when I say Jacobian is basically the differentiation of the variable f with respect to the model parameters, right? So let's say I'm saying that I have n number of model parameters or n number of layers, small n. Okay, so what I'm going to do is I'm going to take the first sample, I'm going to take a derivative with respect to model 1, and then again with respect to model 2, model 3, model 4, and so on. For first time sample I will take a derivative with respect to nth model. Obviously this value will be very small. So for example, if I've got 10 layers, so and I have the first time sample, so that first time sample will come from the closest location, right? So what I want to say here is that if my let's say receiver is placed here and I have got, let's say, 1 2 3 4 5 6 layers, right? And it is recording something like this, right? So this is, let's say, my first sample, right? If this is my first sample, then obviously this will correspond to information coming from this region, right? Whereas the deeper sample will reflect the information from the deeper layer, right? So that means when I do a derivative with respect to the last sample, right, with respect to m1, that will be small, but when I do it with the last sample, last layer, then it will be large. Okay, so that means in this Jacobian there will be many values which will be 0, right? Can you guys understand that many values will be 0 because the upper time samples or the time samples corresponding to T1 T2 might be taking information only about the top layers, right? And the deeper layer information will be there inside the time samples which have arrived later or which have taken more time to travel. So it will take more time to travel from this to this, right? So basically, in general, what we can say is number of data points is equals to receivers into time samples and number of model parameters. So the Jacobian, which is basically a derivative function, which we will look in next lecture why it is very important, it will belong to set of real numbers. In matrix form, it will be nd cross nm, where d corresponds to data points and m corresponds to model parameters. So we have two receivers, 1000 time samples per receiver, 3 model parameters. So nd will be 2 into 1000 equals to 2000, and nm, since we have said 3 model parameters, so it will be 3. So j will have a size of 2000 cross 3, right? So we have 2000 rows and 3 columns. Now we will study what I was trying to explain you through image was, if that in 1D Earth model we have got 3 model parameters m1, m2, m3, let's say that is slowness at 3 depth points, then synthetic data recorded at 2 receivers, that fm denotes the whole matrix, this f1m denotes one vector, and f2m is the recording at second receiver, right? The Jacobian will be like this, 3 model parameters and 2 recordings, each row a data point or receiver, and each column a model parameter. Each entry shows how sensitive a data point is to a small change in a specific model parameter. Okay, now you guys get it? So physically what I mean to say is, when I'm saying del f1 by del m1 is greater than 0, right? That means there is a delays arrival at receiver 1 when I will increase the m1, right? If I increase m1, so del fmy by del m1, basically it is like a change in the value, right? So if the change in value is positive and I change m1, then f1 will increase, so there will be more delay in the arrival. Similarly, if changing m3 has no effect on receiver 1, then how we will quantify it? We will quantify it by saying that del f1 divided by del m3, so basically not divided by, it's a derivative of f1 with respect to m3, will be approximately 0, which I have already explained to you. So here we can see that many values which might become 0. In this case it is very small, but usually the Jacobian is huge, right? So why it is important? Jacobian is sparse in nature, what we have already understood and seen. So it helps to solve the inverse problems, to solve in a much simpler way using mathematical tools, either to increase the convergence speed by choosing a preconditioner, or sometimes it is also used to parallelize the algorithms for solving the inversion algorithm. Okay. Next comes the discretization of the Earth model. The Earth model can be discretized using different methods. We can have finite difference method, finite element method, spectral element method, boundary element method, discrete element method, finite volume method. Okay. And you can see that dimensionality, when I talk about dimensionality, it is basically the forward modeling function which I'm using. It can be 1D, 2D or 3D in nature in all the methods which I have mentioned, but mesh type can be structured or unstructured. So what happens is, as the matrix size becomes huge, we might go for unstructured meshes in order to reduce the computational cost. And also you can imagine that let's say I have got this is my surface, okay, and these are my layers which are almost same in nature, and then let's say that I have an anomaly which is located here, right? So what will happen is that at all these locations I will have a larger size mesh, okay, I will have larger size of meshes. These green lines are indicative of the mesh, okay. But at this location, what I will do is I will have higher density of grids, okay. Why? Because I need to map that thing more accurately, okay, and also to reduce the computational burden on the system. So for example, the physics is not changing much here, right? So there is no use of doing a lot of computation with more number of grids here, but here we increase the density of the grids, and the size of the grids also can vary, so that's why it's called unstructured, okay. If we talk about the accuracy, usually FDM is used, whose accuracy is moderate. FEM is used whenever we have high frequency data. In most of the cases, then we go for FEM method. Okay, spectral element method is used in smooth media. So I can give you an example. When we are trying to study the Earth at a regional scale, then we might go for spectral element method. Okay, and boundary element method is not used a lot in geophysics, but at least at the exploration level, but yeah, we should know about it. And then we have finite volume method, which follows the conservation laws used when we have got permeability, porosity, reservoir modeling, and in those cases it's very helpful to go for finite volume method. Okay, then comes the initialization part. We have got homogeneous model initialization. We have already talked about. We'll say that whole subsurface is similar only, and over iterative updates, basically at different update stage, the layers will start to appear with contrast in the subsurface properties. So for example, there may be a change in velocity or density or whatever. Then we might have gradient based initialization. So we might say the velocity is increasing with depth. So for example, in seismic inversion, we have got well log, which gives such kind of information. It comes under model from other geophysical data, right? So for example, gravity data and even travel time tomography is used to do seismic inversion, okay, for the initial velocity estimation. And then we have got pre-inversion using simplified physics, right? So we might use ray-based methods to generate initial model for, let's say, full waveform inversion. And then there are empirical rules which exist, like Gardner's equation or resistivity depth relationships. There are various charts which are used. Then also what we can do is we can say have a uniform distribution of the subsurface properties. So for example, we know that in a given geological area, let's say if it's a sedimentary area, the velocities might vary from sedimentary area which consists of only sandstone. Then velocity might vary from maybe, let's say, 1500 meter per second to 3000 per meter per second. But let's say if limestone comes into picture, right, the velocity might, or dolomite comes into picture, the velocity might increase drastically to 3500 meter per second. And then we sample from it. Okay, when I say uniform distribution, what I mean is that if this is my probability distribution, then I say that the probability of any layer at any depth has a probability of having a velocity information of, let's say, 1500 meter per second, okay, till 4000 meter per second. Okay, so there is equal probability, right? This basically shows that there is equal probability of any velocity existing at any depth. Another distribution which is used a lot is Gaussian distribution, right? So there also we define that, okay, this is the boundary and this is the, so basically it is defined by the standard deviation and the mean. That is what we give. And then there's uncertainty quantification. We will look into it in detail while doing global optimization methods. Using prior geological model methods, which we already have said that we are integrating geophysical information from other methods. And then machine learning based initializations are also used. Okay, so for example, we might be having some model which is already trained, so it knows how the initialization needs to be done. That has been done already on training, right? It is an emerging area in seismic inversion and facies prediction. Next comes the loss function. When we are trying to estimate the model parameters m such that predicted data fm matches the observed data, so this is a loss function defined on norm 2. Now what is norm 2? We will look into it. So what we will try to do is basically we measure the discrepancy between predicted and observed data, and M is, let's say, an oracle solution, you know. So somehow we know what is that exact solution that helps to minimize this loss, and that is what we are seeking. And M in geophysics, it means it can contain depth information, it can contain P wave velocity information, it can contain shear wave velocity information, it can contain anisotropy information, it can contain density information, it can contain magnetic information, it can contain resistivity information. Okay, and then we have to choose certain minimization algorithm. Okay, now before choosing the algorithm, minimization algorithm, it is important to understand the properties of linear function. So properties of linear function is additive, homogeneity and linearity of combination. So today I'll conclude this lecture here only, and I hope you guys learned a lot. If there are any questions, you can post your questions. Thank you.